Hi, friends of the sun. Welcome to our weekly reading group, which happens every Monday. And you can join these sessions on Zoom yourself with the information that's down in the description. And yeah, in these sessions, we just have an author of some paper that we think is interesting, chat with us and discuss their paper with us. And today it's Janis, who's a postdoc here at MIT, talking about how to train diffusion models on corrupted data. So let's go.
Okay, awesome. Let's get started. So I'll start with the introduction. My name is Yanis Daras. I did my PhD in UT Austin, and I just joined MIT as a postdoc, working with Kostas Kalakis. And today I will talk about one of my favorite research directions, which is how do you learn generative models from corrupted data? And why is that useful? What are like some cool things that could be enabled by such a model? So let's get to it. So I guess like I should not spend too much time trying to convince you that generative models are amazing. They are like very, very good across many modalities. Of course, they have a lot of limitations, but they can do some pretty impressive things that we couldn't do like 2 years ago. So now there's like this question that matters, I think, the most is like, what do you use these models for? So now that we have these very good models, what are we doing with them? So one thing that people like to do with these models is they like to be generating like pretty pictures. And yeah, I'm all for that. That's pretty cool. But another thing that we might want to do is we might want to solve like inverse problems. So what are inverse problems? Inverse problems are basically scenarios where you have missing information. And what would you like to do is would you like to use your model, like whatever knowledge it has for the world, to complete that missing information or give you a plausible thing that could have happened. So for example, let's say that you have like these two robots enjoying their romantic dinner in the first row, and then something spoils in the background. There are like some two other robots kissing, and then you're like, okay, I don't want this. So I'll mask this region, and I will ask my model to infill this missing region with whatever plausible thing the generative model thinks that could go there. So you can do this. So this is like an inverse problem that's called in painting. And of course, like there are all sorts of inverse problems. A lot of them have to do with like personalization that people like a lot. Maybe you see an image, then you get the style from this image and you want to apply it to your image, to your painting, to whatever. And people are doing a lot of cool artistic things around that. But what I'm mostly excited about is I want to solve scientific inverse problems because I think there is a lot of potential there in scenarios where we have like measurements from actual like scientific problems, scientific like settings, and they're noisy, corrupted in some sense, and we actually want to use the prior that the model that we trained has to solve this type of problems. And this appears in like so many scientific settings. Proteins and MRI are like two typical use cases, but there's so many. So let's get to it. So how does it usually work, right? So how does that go? So usually what you do is you collect some training data. Now you have your data set from some distribution that you want to learn. Then you train your generative model. Then you have to decide, like, is it going to be like a diffusion model? Is it going to be like a GAN? Is it going to be an LLM? Like, what is the architecture? So on, what are the hyperparameters? You train your model. And then after you trained it, then you have like an image that has some missing information or some corrupted image, and you're like, oh, you ask your model, can you please fix this for me? So that's how it usually goes. And I want to argue that a lot of the research focuses on these two latter parts. So there's like so much research about like what are the different like learning algorithms, how do we train optimally our models, how do these things scale, and then there's also a lot of research in the space of using diffusion models and these other like models for solving inverse problems. We recently wrote a survey on that, and there are probably like 300 methods here, so it's pretty crowded. But there's not so much research in the first part. That's like a lot harder, in my opinion, which is how do you collect your training data? And I want to like convince you in like the next two meetings, the 2 minutes, that this is gonna be this is like something actually worth thinking about. Because at the end of the day, like the quality of the models that we have is the quality of the data that they're trained on. So if you don't have good data, then you probably don't have a good model. So that's kind of the idea. So what are the challenges in like in the data? So basically, what do we know? We know that like if we want to like train a very, very good model, then we want a high quality large data set. And this can be hard to acquire for a couple of reasons. So the first reason is like physical constraints. So what does that mean? when you train like a text-to-image diffusion model, like DALL-E or Imagine or whatever, you probably have like 12 billion images in your dataset. But in scientific applications, you cannot afford this because sometimes it's actually expensive to get data, like in the MRI case, or in like proteins, you have to go to the lab and crystallize the protein. Or sometimes it's even impossible. Let's say that you want to do like black holes, like good luck getting a good image of a black hole. This is something that you can't do. So in these settings, we don't have like such abundance of data. For example, MRI, we have less than like 7,000 fully sampled brains, and this is the go-to data set. This is like the fast MRI data set where people go and train on it. And for proteins, this protein data bank is the go-to data set, and it has like 200,000 model structures, which is nothing compared to like the 12 billion structures that like the 12 billion images that people would use to train a text-to-image model. So this is like one problem. The other problem is that, you might have a lot of data, like in images, but then your data are also not perfect. For example, you have some images that are like compressed with JPEG, or maybe you have some blurry images, you have some noisy images, some images with like color artifacts and stuff. And then like when you have these images, you are faced with a dilemma, you're faced with a choice. And what is this choice? What can you do? You can throw them away, and then you don't risk like having bad samples in your data set, but then you throw away so much information. Like for example, this image of the dog, you can still see that there is a dog, and then the other image you can see that there is a girl, and there is a tree. So all of this information is there, but you throw it away just to be safe because you don't want to be generating blurry dogs at inference time. Or the other thing that you can do is you can keep it, but then you like risk having a generator that's like producing bad things at inference time. So in settings where like you are not data limited, then you can afford throwing away a lot of your samples. But in some settings where you are data limited, you cannot afford to do this. Cool. And then the other thing is like sometimes your images, for example, text-to-image models, they are pretty good, but the captions are really bad. So the type of corruption can be like really arbitrary. And this is like most of the times the case. For example, we did this project Datacomp. We're trying to create like a very big data set, the follow-up of Lion. And then we ended up throwing, like, I think we downloaded 100 billion images, and we ended up throwing away 70% of them just because of these text-to-image, text and image like misalignments. So a lot of corruptions. Final reason, and then I'll get to the point of how do we solve all of these problems, is that like diffusion models in general memorize a lot. So here's like a fun little experiment. You can train a diffusion model on like a limited data set, like 300 images. Then you generate a couple of images, and then you look at the nearest neighbor in the data set. And what you ended up seeing is that you basically, congratulations, you just invented like a copy machine. And any reasonable person, I think, would argue that this is like not useful. So what would you like to do is you'd like to generalize, but the network just overfitted to this training image because you didn't have a lot of them, and this is what you ended up getting. And I hear your complaint. Maybe what you're gonna say is that like, look, like the setting of only having 300 images is not realistic. We can like have more images, blah, blah. But this actually happens at scale. And we have this other like fun experiment. So there's this data set, Stable Diffusion Excel, that was state of the art like 6 months ago, but who keeps track? Maybe now there are like 3 models that are better than this. Well, anyway, back in the day, this model was state of the art, and they didn't disclose the data set. And then we had a hint that maybe the model was trained on Lion that has a bunch of problems, and we wanted to test this. So here's our test. We took an image, this is a real image from Lion. And then what we did is we put a big black box covering the face of the person. So we have these masked inputs, like an image that like has like a very big black box that we want the model to infill. So again, yes, we want to use the prior of the model to infill this image. And this is the result. This is what you get. So basically, the model not only managed to infill this image with a plausible completion, but it just happened to be the case that the completion matches exactly what we had in our training example. And this is not a cherry-picked example. It actually happens with a lot of images. And I think it's a very compelling evidence that these models, even if they're training like billions of images, they still get to memorize a good percentage of their data set. And this can be problematic. So yeah, so we have all of these issues, the physical constraints, the dataset curation decisions, and the privacy. And a lot of these things could go away if you had a way to train with corrupted data. Because for example, in the dataset design, like example, you wouldn't throw away like this image of a dog, of a person, of the tree, because you could treat them as like corrupted images and use them in your pipeline. So the idea is here that like all of the samples matter, but they're not equal worth. So some samples are better than others. The ones that are not that good, you should not throw them away. You should still use them. But when you design your algorithm, you should know that this sample is corrupted and treat it as such. So there is this need of like designing better training algorithms that can leverage all of these samples. But these algorithms need to account for the fact that some of our samples are corrupted. So I hope I convinced you that this is important. And I hope I did it because that's going to be the focus of today's talk. So today we're going to talk about this interplay between what happens like when your training data are corrupted and how do you need to adjust your training algorithm to basically account for this fact. And listen how this is going to go. We're gonna start with a very simple, like theoretical toy example, which is what you do when your data has been corrupted with additive Gaussian noise. So we are gonna be in a setting where we never see like a clean image. All of our images are corrupted, but in a very special way. They have additive Gaussian noise. And then we're gonna start relaxing it and make it like more and more realistic and more general and more broad. So the next relaxation is gonna be, okay, what happens when not all of your data are corrupted, but maybe some of these data are corrupted and some of them are not? How do you account for this heterogeneous data kind of setting? And then we're gonna say, okay, but like Gaussian noise was like such a limited example. Like realistic corruption, not Gaussian noise. So maybe let's be a little bit more general and we'll be able to do like linear measurements. And then towards the end of this talk, I'll give you some hints about how you could generalize this to arbitrary corruptions, which is like an ongoing direction I'm actively working on, and I'm super excited. So if you want to elaborate on this type of stuff, I would be super happy to talk with you after the talk. So that's the plan. Let's get to it, because as you can see, we have a lot to cover. So let's start with like the fully corrupted data setting. And let's see how do you normally train a diffusion model. So normally when you train a diffusion model, you start with some clean images. Here, for example, is an image of Professor Toralba from MIT. And then what you do is you noise it at different levels. And then what do? Like at a specific noise level T, you're gonna train your model to predict X0, the clean image, given XT, which is a noisy version of X0. So that's how you normally do it. And then, if you do everything amazing, you have a very powerful model, a very good optimization algorithm and all that stuff, you end up learning the conditional expectation of X0 given XT, which is the minimizer of this loss. Cool, so far so good. But now that's actually like not the case that we're gonna look at. We're gonna look at the case where there is some time T. We're gonna call it T nature. And basically what we are gonna think that's gonna happen is that there is some wall and we cannot see images on the right of this time, which means that we cannot see clean images. We only get to see like these noisy images, and of course we can noise them more and create more noisy versions of them, but we can never see like a clean image. And then under this setting, we are still very interested in learning the best denoiser, which is this conditional expectation of X0 given XT, for all times T. And that includes things on the left of that wall, that includes things on the left of this T nature, but it also includes things on the right, where we don't have any data at all. So both of these problems are gonna be pretty hard, but they're gonna end up having some very simple, elegant solution. And they're different. I want to actually like emphasize this. These are very different problems. One problem is like, okay, I have a very noisy image and I want to remove all of the noise, but I can generate a bunch of those like noisy images, and I want to like learn to reverse that noise. On the other setting, when you're gonna go to the right of this teenage, to the right of that wall, you don't even have clean images. You don't even have inputs for which you're trying to find the denoiser. So in one setting, we have inputs, we have the noisy images, but we don't have the target, we don't have the clean image. That's on the left. On the right, we don't even have inputs. And of course, we don't have the target. But it's still going to be feasible to do this. And that's kind of surprising, I think. And it's going to be the basis of the techniques that we're going to develop. So let's start with the easier problem. Okay, so just to see it visually, there is this wall, this T nature, this is the red dust line. And what you want to do is you want to learn the denoiser at this other time T has more noise, which is illustrated with this white dust line. So that's the case. So now I'm gonna talk about math for only one slide. I promise you. So I want your attention for this one slide because it's actually a pretty simple idea. So I think it's worth like going over it. So here's the idea, okay? So we have this XT, this is our noisy image. And there are two alternative ways to view this noisy image. You can view it as something that was once very clean, this X0, and then you added a lot of noise to it. Or you can view it as something that was like noised at a particular noise level, this red dashed line here, which we were gonna be calling XT nature, then the noise level what we have in our data set. And then you just added a little bit of noise on top of that. So these are two equivalent expressions for this like random variable. It's just a noisy version of two other random variables, either a very clean random variable or something that was like a little bit less noisy. And now there's this wonderful result from statistics, which is called Tweedie's formula, that basically says something like kind of surprising, I would say. It says that like whenever you're in a case where you have something plus Gaussian noise, and you care about like the score function, the gradient of the log likelihood of your y variable that has been noised, then it turns out that this score function has a very straightforward connection with the best denoiser of x, of the thing behind your corruption, given this corrupt observation. It basically tells you that like, if you care about the score function, then you just like need to find the best denoiser of your clean image, given this corrupted observation. It's not immediate obvious how this relates to the things that we are talking about now, but it's gonna become obvious in a bit. So Hannes, you have a question?
Yeah, so this Tweedie thing, doesn't it just say if we have a point, now we drop a Gaussian around it. So we have this like Gaussian thingy. And
Yeah.
then the direction of steepest density ascent, like where we center our Gaussian around, because that's where we drop the yeah, because that's the original point that we add some Gaussian noise to. Like this direction of steepest ascent, so the score as well,
Mhm.
that is just going to the original. Oh no, yeah, going to where you came from, going to the thing that
Yeah.
you added noise to.
So I guess that's one way to view it. I would say that adding to what you said, that like when x, the random variable x, has a very has like a Gaussian distribution, or it is like a Dirac, as you said in your example, then this result is pretty straightforward. What is surprising is that this holds for whatever distribution x has. So this holds for arbitrary distributions of x. So x, like in your example, was just Dirac, or maybe it is like a Gaussian, and then you add more noise, you have
Yeah.
another Gaussian. But this holds for arbitrary distributions x. The distribution of x can be arbitrary. The only thing that matters is that y is a noisy version of x. That's all I want.
Okay. So kind of, so this PT is a noisy distribution or a noisy version of the distribution of the axis.
Yeah, which can be arbitrary. So the
Yeah.
distribution of the x can be arbitrary, so that means that also the PT of y is also arbitrary because that's the noisy version of this distribution.
Okay.
And this result holds. So I guess what you said is perfect because you give the intuition. If x was a Dirac or if x was a Gaussian, your intuition directly works and everything checks out. But the surprising thing that this works for arbitrary x's. Cool.
All right. Yeah.
So moving on. So thanks a lot for this question. That was engaging. Now let's see how this is useful in our case. It is useful in our case because we can actually, this holds for like y being a noisy version of something, but our xt is a noisy version of two things. It's a noisy version of x0, and it's also a noisy version of xt nature. So what this means is that we can basically apply this thing twice. So we just take this formula, and then we apply it twice. And what do we get out of this? We get two equivalent versions for this core function. Both of these expressions are valid, and they're actually equal because the likelihood didn't change. The same random variable has the same likelihood. And that means that like by applying to this formula twice, you can get like two equivalent versions of the likelihood. And if you equate them, you get this result. So let me walk you through it. It tells you something like kind of surprising. The first time I saw it, I was surprised. Then after this, in retrospect, I was like, okay, maybe that's not that surprising. But it basically tells you that. So on the left hand, you have this conditional expectation of x0 given xt. What is this? It is the best denoiser that removes all the noise. Remember, xt has a lot of noise, and you care about removing all that noise. So that's what you want to learn. And this is the object on the left, this conditional expectation of x0 given xt. And this result that we just proved here, it basically tells you that if you care about removing all the noise, you just need to remove a tiny bit of noise and then just have some like affine transformation. Because the object on the right, this conditional expectation of xt nature given xt, just removes the extra noise that we added on top of what we had in our dataset. So it basically tells you, if you know how to remove a little bit of noise, then you basically how to remove all of the noise. And then basically what people were doing before is they were saying, okay, like I want to learn to go from this xt to x0, but now we don't have x0, so we cannot really train for this objective. But what we can do is we can train a model that removes the extra noise that we added. So this is like this model that's trained like this. So this model is just basically trained to go from like xt to what we had in the data set that was already noisy. And then if you have this model, this denoiser that just removes this tiny bit of noise, you can plug it in the formula that I had before and get this denoiser that removes all of the noise that there is. And this basically kind of solves your problem, because if you want to go all the way back to like 0 to clean images, you just need to remove the extra noise that you added that was like from this nature onwards. Does that make sense? If I don't hear any complaints, I will assume it makes sense, and maybe you lose me. So take a risk. Okay, cool. I'm very happy. Hopefully you're with me. And then cool. So we solved the problem for the left part, which is half of our problem. But then we still have to show like, how do we solve the problem on the harder setting, which is like, we also want to learn the denoiser in this like regime right of this wall, right of the nature, but then we don't have any data at all. So what do we even do? Of course, we cannot apply the same idea, because before the fundamental concept was that we had something that was like a little bit of noise and then we added further noise. But now we want to apply this to something that like we don't have some version of it that's like less noisy. We're just gonna go like below the noise level of the dataset. So for that, you're gonna have to like my definition of a consistent denoiser. And I'm telling you that you have to like because I came up with it. So I don't want any objection to that. I hope you like it. The way, like, I think it's better understood visually. So let me tell you what is a consistent denoiser. Okay, like with this simple visual. So let's say that you have like some noisy image. This is your teenager noisy image. You have managed to arrive there so far because you did the previous trick. And then now you have this denoiser h theta, and you ask the denoiser to predict you all the way up to 0. So it gives you this blurry image. So the reason this image is blurry is because there could be many like clean images that would give you this noisy measurement. So it kind of averages them out, like all of the potential like clean images that could correspond to this noisy measurement. So cool, we keep that prediction somewhere aside. We know that it's blurry, that makes absolute sense because there could be many things that could have happened. So we keep this prediction. Then what we do is we keep running our sampling with this model that we are trying to train. And then with this model, we get like these two other like points at this other time t prime. They're still noisy, but they're like far less noisy because we run our sample and we denoise them. So we have these two other images. They're still noisy, but far less noisy, and they are different because they're stochastic in the sampler. Every time you do this, you start from the nature, you follow a stochastic sampler, so you arrive at different points. Both of them are a little bit noisy, and they're different. And then what you can do is you can like ask your model again to give you the prediction for each one of these points. So you get like now images that are like less blurry because the initial noise that you started with was lower. So you get these two different predictions that are like, both of them are like seem like clean images, and they're far less blurry than the original prediction. And now your denoiser is consistent if the average of these things matches this initial blurry prediction, which means that basically, if you care about having a consistent denoiser, you can basically train for this objective that basically says, okay, I have this noisy image, give me your one-step prediction, that's h theta of xt nature. That's like this blurry prediction on the top. And then you're like, okay, I'm gonna run my sampler, I'm gonna get these different T primes that are like less noisy versions of my starting image. And then I'm gonna ask again the denoiser, what do you think the clean image is? I get one prediction, two predictions, three predictions. I average them out. Because of this averaging, I
I
also
have
end up,
sorry.
yeah,
Uh, Sorry to interrupt. So is this the assumption that the first MMSE prediction that you get from the full noisy observation, that is the best, that has like the perfect model at that stage, right?
that is
If
correct.
that model is not good, then you will end up with something which is not the correct estimate of the MMSE, and then this entire setup might give you a wrong output. So in terms of scientific images, how would you kind of solve
Right.
that? Yeah,
Okay.
thanks.
That's perfect. That's perfect. I think this is a great point. So what you are saying is that being consistent doesn't mean that we have a good solution. Why? Because let me tell you, my favorite consistent denoiser is the denoiser that always predicts zero. So this is consistent because h set of x in nature, zero. Then I did nothing, and then I again predict zero. So that's consistent. But of course, this is not satisfying like what we want. Now, here is our result that I think is nice. It tells you that like if you managed to do very well up to this nature, which is exactly as you said, like all of this assume, like now we will assume that up to this nature, we managed to do perfectly. So we managed to get a perfect denoiser up to this wall because we had a way of training this model. It actually was very similar to how you would train a normal diffusion model with this little trick that we did. So if everything went fine, and then you are consistent, then we are proving that the unique way of doing this is to actually find the conditional expectation of x0 given xt everywhere. So to answer your question, yes, there could be many denoisers that are like consistent, and some of them are really bad. An example of this is like the denoiser that always predicts zero. But then another denoiser that is consistent is the denoiser that we are actually looking for, this conditional expectation. It's you can show that this conditional expectation will actually make this loss zero. So we have like one denoiser that's like the all zeros prediction, which is a really bad denoiser. And
Could
then we
you
have
please
this other
point in the slide? Could you please point the denoiser that you're talking about? Because yeah, because I was getting a
okay, cool. So let's see
sorry.
if I can do this. It's actually not very easy to do this, but let's see. Maybe I'll try. So, okay.
Yeah.
So, okay, what I'm talking about is that like, let's say that this h theta here predicts like zero, okay? Then you
Right.
will have like a zero prediction, then you run your sampling, whatever you arrive here, you also run your h theta, you get a gen zero. So then you have like a consistent denoiser, but that's a pretty useless denoiser because it always predicts zero. But then what we would like to learn is we would like to learn this like conditional expectation, right? This is the denoiser that we care about. And normally we train this denoiser by running like by running the normal training of diffusion models. But in this particular case, we can't do this because we don't have data. We don't have targets to train this. But let's say somehow that like we manage to get this. If we manage to get it, we'd make this loss zero. This is like a fun little exercise to do. If you work out the math, you will see that this like the denoiser that we are looking for is a consistent denoiser. So there is one denoiser that we are looking for that like would make this loss zero. And there are many other denoisers that are like not the one that we are looking for that would also make the loss zero. Now, the result that we prove is this one, that like if up to this point, if up to this wall, you managed to perfectly learn the denoiser so far, and then you manage to be consistent for whatever is like on the right of this wall, then there is no many solutions. There is a unique solution, and that unique solution is what we are looking for. That's kind of the
No, but
nature of it.
from the wall, the TN, the T nature wall that you're starting
Yeah.
from, the perfect denoiser is your MMSE estimate, right? So how are you defining like, so you, I'm not sure if I am
Yeah.
able to
So
convey my
no.
issue.
I get your question. I think you're saying that like yes, the teenage denoiser has to be the MMSE denoiser, which is this conditional expectation.
Yes,
Now,
yes.
like basically, the first prediction the model does at nature should be perfect. Now, maybe
Mm-hmm.
you're asking me, how do I guarantee that this is perfect? It's because I train with this combination of the two losses. I train with this loss here, that's consistency loss, but I also trained with this trick that I had before that was like basically training the best denoiser up to this point. So because there are these two losses, like up to nature, the previous laws was like guarantee you that you will find the best thing if you have enough computation and enough, like you have a good optimizer and all that stuff. So the other loss is basically forcing you to learn the best in nature. And then given that, the only way to be consistent on the right of this wall, on the right of nature, is to actually continue to have this conditional expectation. That's kind of the nature of the result. Cool. Like we can take more questions about this on the end of the talk because I want to kind of move on. But I guess that's like the most math heavy part of the talk. But just to zoom out, what basically we have developed here, we have developed a tool to learn the conditional expectation of x0 given xt for all time levels. So we have basically developed a method that can learn a diffusion model without any clean data, in this case of like additive Gaussian noise in the corruption. Now let's see if it works, okay. So to see if it works, we first did this experiment. So we said, okay, let's start with this stable diffusion Excel model. Then we take an image, and then we will like, that's an image of the data set. And then what we will do is we will encode in the latent space of this model. Then we'll add a lot of noise to the latents. So we have like different noise levels. So one is like no noise. That's the first image. I'm showing you the encoding of this initial pixel space image in the latent space. Then the second column is like what happens when you add a little bit of noise. Then you have a lot of noise, and then you have like a lot of noise. And then we do this for all the images in the data set. So we created these like noisy versions of them. And then we only train now with these noisy versions. And just to give you an understanding of like how noisy are these noisy versions, if you were to actually have like the perfect model, if you were actually to train with clean data, and then you started with these like noisy latents, and then you did like the posterior sampling and all that stuff, you would get images that you see increasingly they're becoming like more and more distinct compared to the one that you started with. But now we're not going to do any of that. So we're only going to use this row, the noisy latents, and we're going to train with our tricks and the noisy latents. And for the very first experiment, what I'm going to do is I'm only going to train the model up to this wall. And then when I am to this wall, I'm just going to give you the blurry prediction. So I'm going to see the effect of like training up to this wall. And then after the wall, I'm just giving you the one-step prediction that it will be a little blurry. And I want to show you what this means. So let's do this. So we did this experiment, and we did this experiment at like different noise levels. So the first row is what happens when you train the model with no noise. Like you just saw the latents the way they were, you didn't add any noise, and you see that you get like pretty good pictures that they look fine. They're just like, these are not real people. These are like all fake people, and they look okay. Then you add more noise. This is like the second row, and then maybe you see some like difference in quality, maybe not that much. But then as you increase the training noise, you will see that like at the end of the day, you learn that the noise that basically gives you these like ghost-like images. These are like images that are like, they look like ghosts because they're average across all of the things that could have happened using this noisy latent, and these are pretty bad. And then what we do is after we train this model, we're gonna say, okay, now we'll train for the times on the right of this wall, on the right of the nature, and then see how much of the details we recover. And you basically see here are the results on the right, and you will see, of course, there is some quality degradation because when you trained, your data set was like really noisy, but now the image become a little better, and you managed to recover a lot of these details. Now, of course, this is like very hand-wavy because I'm just showing you pictures just to give you a sense, but you can also like measure this. So what you can do is you do different trainings with different noise levels in the training, and then you can measure FID, and the lower the FID is, the better. So if you just train without any noise, you basically get some performance. And then as you increase the training noise level, the performance increases. The blue line shows you what happens when you don't train on the right of the wall, on the right of the nature. And the orange line shows you what happens when you do actually train on the right of the wall as well. And what do we see here? We see that the model is actually like pretty robust up to a certain corruption. So, there was some increase in, like there was some deterioration of performance, but it wasn't that bad. So we went from noise level 100 to noise level 500. The model managed to keep most of its performance. But at the moment you like overdo it with your corruption in the training, then this starts like behaving really bad. So there are like some regimes where this kind of works, and there are some other regimes where this doesn't work. Of course, you need both of these like trainings on the right of the wall and the left of the wall. to get the best results. But still, even if you do this in practice, if you have so much corruption in your training data, this is kind of gonna be limited. So that's the first thing that we observed. We observed that this like will work up to a certain corruption in the training, and then at some point it's gonna give you very bad results. First fact. Second fact is like what is gonna happen in memorization. So I mentioned at the beginning of this talk that when you train models with clean data, they memorize. So, but now we just train with noisy versions of our data. So did it memorize or did it not? So for that I have this plot. What do I show here? So what do I do is I generate like 50,000 images from my model, and for each one of them, I look at its similarity to the nearest neighbor in the dataset, and I plot you these similarity curves. So the blue curve is what happens when you train with clean data. The orange curve is what happens when you train with noisy data. And what you can see is that the blue curve shifted to the left when I train with noise, and that's how you get this like orange curve, which basically means that training with noisy data reduces memorization of the training set. So you see this tail with a has similarity above 90% on the blue curve. This is basically all the images that you completely memorized, and this is getting disappeared when you train with noise. Because your model can't memorize them because it never saw them. So it's kind of impossible to memorize something that you never saw if the corruption was really, really high, and there wasn't any way that you could actually reverse this. And then of course, this was like just with faces, but we could train a model with like basically text image models like the other ones, and you get some reasonable results as well. So this kind of works. Then maybe you say, okay, all of this worked because like you fine-tuned, and then what happens when you train from scratch? And then we did that. So we trained from scratch. This is like part of our newer work that we have. And basically, so what we did is like we took a bunch of data sets, CIFAR10, CELEBAY, and then ImageNet. And then we trained models at different noise levels, from no noise to like a lot of noise. And then we started like observing what happens with performance. The first column that I saw this truncated sampling was when you like just do the one-step prediction on the wall. And the right one is like what happens when you train with like this consistency to even get the best denoiser on the right of this wall. And again, what does this show? It shows that like, you know, it kind of works when you have like mild corruption, but when you have like high corruption, it kind of like, it's probably like not giving you the performance that you would hope. If you are operating on a scientific setting where you don't have any clean data, that's probably the best you can hope. And then, you know, like train with this and hope for the best. Now, if you're in some other setting that you have some clean data, basically just training from noisy data, it's not gonna do it because there's gonna be some performance hit that you're gonna have. And the higher the noise level in your training set, the higher this performance hit is gonna be. You win some memorization, but still you lose some performance. And then of course, like this consistency thing is like kind of slow as well. And all of the results of like learning the optimal denoiser would hold in the infinite limit of like having infinite data, infinite noisy data, which doesn't work. And in practice, it leads you to this performance hit. So yeah, so we were at this point, and then we're like, okay, so we have developed a method that works in this very toy setting of additive Gaussian noise, and it has some nice math, and we managed to do some good things, and it kind of works. But people were like not as excited because they were like, okay, yes, I can use it, but then now my performance, the performance hit that I got was too high that doesn't justify like this memorization thing I want. So we're like, okay, typically people train models when all of your data is corrupted. So this is like the regime where people train models on. Then what we looked at is what happens when like all of your data is, sorry, people train models when all of your data is clean. And then what we looked at in the previous slides is like what happens when all of your data is corrupted. So these are two extremes, you know, either all of my data is clean or all of my data is corrupted. But the most realistic setting is that like each one of my data point has a different level of corruption. So you could be like more in a setting like this. So, you know, you don't have a single wall, but you have many walls depending on your data point. So each data point comes with its like corruption level, and then you want to kind of leverage all of your data points that come with different corruption levels. So this is heterogeneous setting is more like what happens in practice. And we'd like to see, you know, does this change anything? You know, before, like we had this thing that we had the nice math results, and then we had the thing kind of was working after a certain corruption, but with high corruption, it was not working. And then we're like, okay, what if we have some clean data? So here's the setting we're gonna briefly look at. We're gonna say that we're gonna have two sets. One set is like all of my corrupted images, they're gonna be at this teenage noise level, and then maybe I have a lot of corrupted images. Maybe, you know, I managed to find a lot of corrupted images from the web, and then I also paid some third party or did a lot of effort to get a few clean data points. So I have a few clean images and I have a lot of corrupted images. So that's the setting I'm gonna operate on. And then, like, here's the algorithm, you know. On the left of this wall, we're gonna use all of our data. Both of the clean images and the noisy image are gonna be used on the left of this wall, using like these tricks that I had before. On the right of this wall, we're not gonna do any consistency, that slows us down. And since we have some clean data, we don't need that. So we're just gonna use the clean data. We don't have a lot of data points there, but we're just gonna use the clean data. And then we're gonna see what happens, okay? So this is the most surprising result for me. So let's understand this simple result. If you are to take away one message from this talk, I think that's the message you need to see. So we train models on 3 data sets, CIFAR10 CLB ImageNet from scratch. And then the first setting that we looked at is what would happen if we had 100% clean data. So if you had 100% clean data, that's the best thing that you can get. And then you have like these performances. So that's your limit. Then we say, okay, what happens when you have 100% noisy data at a certain corruption level? And then you see that the FID performance goes from, example, for CIFAR10, it goes from 2 to 12. For CLB, it goes from 2.4 to 13. From ImageNet, from 1.41 to 5. So the moment, you know, you still have a lot of data, but all of your data are noisy. And then the performance is pretty bad when you only train with noise because the noise level is very high. Then we said, okay, what if we have clean data, but we don't have a lot of them? So let's say, let's train on this smaller data set that has like 10% of my total data set, all of my points are good. And then you see that like the performance is also pretty bad. So either training with a small clean set or training with a big noisy set, both of these things give you very bad performance. And then we're gonna do this little experiment where we train with a mix of 90% of noisy data and 10% clean. So you see what this means? It means that basically the majority of my data is noisy. And I have a few good data points. And then I get performance that's like pretty good. It's like almost as good, a little bit worse compared to what would happen if I had 100% of like clean data. So that's pretty surprising to me because training with the clean data alone was super bad. Training with all of the noisy data in the world was also super bad. And then the moment I mix them, the moment I have a few good data points and then tons of like bad data points, I get very good performance. And then I was like, okay, I need to study this better. So what I did is I got obsessed with it. So we trained like 200 models. I'm not kidding. We actually spent a lot of compute on that. So we trained a lot of models at different combinations of like how much noisy you have and how much clean you have. So some settings we have like only noisy, in some settings we have only clean, in some settings we have a little bit of clean, a little bit of noisy, all sorts of models. So we did this. And then we started like getting basically performances for all these settings, and we're putting them in the data, and we're putting them in a table. And then let's look at what this gives us. Okay, let's look at these two numbers that I saw here. So the first number, this like 1.65, is what you get when you train on ImageNet with 70% of ImageNet all clean. So that's basically what you get. Like, if you take ImageNet that has like 2 million samples, you keep 70% of them and you train, you get this performance, 1.65. Then this other number, this 1.51, is what you get when you take ImageNet, you split it into 2 halves. 50% of them you keep it as is, and the other 50% of it you add a lot of noise. Then you train a model with this mix of noisy and clean, and then you get this other performance, 1.51. Remember, like lower is better, so that means that training on a mix of 50% clean data and 50% noisy data is better compared to training with 70% clean data. So you can get this inequality that says like, okay, if I were to assign a price for my clean images, what would this price be? And then you know that this price would satisfy this inequality. It should say that like 70% of clean images gives worse performance than 50% clean images and 50% noisy images. And if you do this extensively, you can get like inequalities for the price. So for example, this would give you that like the clean image should cost less than 2.5 times the noisy image. And then you can do this extensively all over the table, and you get something like this. For different noise levels, you can perfectly characterize what is the price of noisy images, which means like how much less useful noisy images are compared to clean images. And you get something really surprising. You get the fact that like the moment you have a bunch of like clean images in your data set, now noisy images are not that useless. Actually, they're like almost as good as the clean images, because like, you know, even in the extreme corruption of like sigma 0.2, that's like a lot noise. If you visualize it, you will see like a lot of noise. You see that like the price of a clean image is like at most 1.75 times the price of a noisy image. Now, if you don't have any clean data, that changes completely. If you don't have any clean data, noisy images seem useless. You might need like 10,000 times more clean images to get the same performance as clean images. But when you have this combination, this mix of clean and noisy, things behave much, much nicer in favor of noisy images. We have some theory of that, but I won't go over it. What I briefly want to go over is that like these kind of things kind of generalize to other types of measurements. So far, I only talked about like additive Gaussian noise, and the idea, part of the idea was like, oh, we have this image that has noise, and then we add more noise. And then this thing, you can do it also with linear measurements. So maybe you have an image that like 95% of the pixels are missing. What you can do is you can like make the pixels that are missing 96%, but you're going to hide from the network which pixels are actually missing from the beginning and which pixels you are kind of like masked on top of it. Or maybe if a box was missing, then you add another box that is missing. So you create this other corrupted input, and then you, again, you don't tell the network which box was always missing and which box you made missing. So the network is kind of incentivized to predict the clean image without any corruption. So we have some theory for that, but yeah, results. On the left, you see training data. They have like here in the left, you have 50% of the images, they have like 50% of the pixels are missing on average. On the right, you see the generated images. And as you can see, my generated images, they don't have any missing pixels. So my model managed to actually be able to generate images without missing pixels, even though it never saw an image that was like a whole. And then I increase the corruption, and then still it works. And then I increase it more. So I managed to train these models that are like 90% of the pixels are missing, and then we went to the extreme. We trained with 95% of the pixels are missing. The pixels are missing, and then you still get pretty reasonable generated images. Again, same thing as before. When you only train with corruption, what happens is that your performance gets worse and worse, but your memorization goes down. Now, if you have a bunch of clean data points, then you can use them, and you kind of get around this issue of performance going down, and you get the best of both worlds. So that's kind of it. A cool application of this is that like you can now train with like limited data, because if you have a limited data set and then you train your model on it, what would happen before is that like you will just get a copy of your training set. But now if you use our algorithms and you don't train your model just overfit your measurements because they're bad, and you train with corrupted training images, you manage to kind of generalize. So we kind of unlock this application where before, if you had a limited data set and you trained there, you just basically get copies of your data set. And now if you like make these images noisy, your limited training set, you make it even noisy or corrupted in some sense, and then you train with our algorithms. Surprisingly, now you can like learn to generalize. It's some sort of augmentation, but now the augmentations are not leaking. So it's like this corrupted
I have a small question here. When you say the exact copy of the data set is memorized, so do you mean like in terms of MSE, pixel-wise MSE, or just from the appearance?
Both. So we measure like we just what we do is like we take these images and we embed them in some space. Maybe you embed them with Dino, and then you measure like cosine similarities in this embedding space. So the plot on the right here is basically shows you this like distribution of similarities, and the red curve is what happens when you train with like not with clean data, and the blue curve is what happens when you train without clean data. And the thing with clean data, you see that there's this tail on the right of 0.90 similarity, which corresponds to just basically memorize things.
Right.
But when you train with like under corruption, this doesn't happen. You shift on the left, so you have less memorization. And then you can visually go and see like, okay, what are these points that got the most memorized according to Dino? You take these points, you visualize them, and that's what the thing on the left is showing.
Okay, thanks.
So yeah, both visually and like some sort of like similarity metric, not MSE. MSE is not very robust. So what we are reporting is like similarity in some embedding space, which is Dino. Cool. So with that, I will almost wrap up. I'll spend another 30 seconds to basically tell you about some ongoing work on this. So what is missing is a question. So we have like a framework that can do a lot of things. What is missing on this framework? And if you ask me what is missing for this framework to get like more adopted and more like to have like more widespread usage, is basically this framework is limited right now by the type of corruptions that it can deal with. So most of the talk we talked about additive Gaussian noise that was very limited. And then now we're talking about linear measurements, like this in painting example, but still like real images, real proteins, real MRIs can have like also other sorts of like corruptions. I guess MRI is better, but like proteins and real images, they have other corruptions. So like the question is like, can we generalize kind of these techniques? To this more general case. And then for that, I will just give you this, I will play a game, okay? It's gonna be a little game. And the game is gonna be the following. So on the left, we have a clean image of Antonio. Again, Antonio is a professor at MIT. And on the right, we have a corrupted version of this image. That's like a blurry version of it, okay? So now, of course, you can tell me which one is which, okay? Like if I ask you which one is the clean image, you tell me, oh, the green one is like the clean image, it's pretty easy. But now what we can do is we'll start adding noise. And then I will ask you again, like, can you guys tell which one of the two is like the clean and which one is the noisy? Anyone want to guess? Like, is it the left the clean or the right?
Right.
The right is the clean.
Correct. Boom, you won the game. But now I'll add more noise. So one of them is like the noisy version of the blurry one, and the other is the noisy version of the clean. Can you guess?
Left.
The left is
Left
the
is
clean. Okay. Okay. Now we have some disagreements, and who wins is Hannes wins. But now Hannes, I'll make it like harder for you. Can you now tell? And for the rest of the people as well.
the left.
The left is the
Left.
clean?
Yes.
Okay, you're a pretty good classifier, correct. But the point is that this task is like becoming harder and harder even for humans. So, you know, maybe you have some arbitrary corruption, but the moment you add Gaussian noise to it, now the corruption is like not as arbitrary, because even if you started with some like blurry image or some image that was corrupted in another way, under a lot of noise, this basically becomes indistinguishable from a clean image plus noise. So what this motivates is this kind of approach, where like you have some corrupted image, and what you want to do is you want to basically see how much noise do I need to add to make it indistinguishable from a clean image. So that's the kind of decision that you get. And the moment you do this, you can apply all of the techniques that we had. So even though our techniques could only deal with like noisy image that had additive Gaussian noise, now you have your new image that is like not additive Gaussian noise, some blurry version of it or whatever. And then all the thing that you need to do is you need to tell me how much noise do I need to add to make it look like a noisy version of a clean image, and then you use it from this point onwards. So that's how you build the wall. And you can train a neural network to do this. I won't get into the details for the sake of time, but there is some like easy extension of this idea to arbitrary corruptions that we are actively investigating. So cool. That's kind of it. Conclusions. So we developed this framework that can train diffusion models with corrupted data. This is very useful for a variety of reasons: scientific applications, reducing memorization, and making the best use of our data. When we have a lot of data that some of them are not that good, we don't want to throw them away. We want to get the information that they have. Now, if you don't have any clean data points, it usually leads to some performance hit. So, you know, if you are doing black holes, then yes, use it. If you're not doing black holes and you're doing anything else, then I would say invest some time getting some clean data points. Because the moment you have a few clean data points, now this framework, it is as good as training with a lot of clean data points when you do it with this mix of like a few clean and a lot of noise. So currently it only works with like toy corruption models, additive Gaussian noise, and then these linear corruptions, blur in painting and stuff. But I gave you a hint about how this would generalize to more arbitrary corruptions, and the underlying math should not change too much. We're actively exploring this, and thank you so much for your time. If there is time for questions and you guys have questions, I will be happy to take them.
Thank you. Yes.
I have one question if there's time, or Hannes, if I was going to say, wait, could we go back for a sec to the slide about like minimizers for the consistency loss. So my
Yes.
understanding, I don't, so apologies if I'm getting part of this wrong, but it seems like roughly this is I think one slide to the right, or one or
This
two.
one?
Yeah, this one.
Yeah.
So self-consistent. Okay, so self-consistency is weaker than I've learned to invert the convolution. I was basically going to ask about, like, in general, like, do we know that convolution is invertible in this case? Like, it seems like it could be that if I only train with if I have no clean samples and I only train with noisy things, then there's like kind of a loss of information, and it's impossible to recover some of the higher fidelity details in the actual data set just because there's no unique inverse to this convolution.
Perfect. So that's an amazing question. Great, thank you. Exactly. So basically what happens is when you add noise, no matter how much noise you add, there is an information theoretic argument that you can always perfectly recover the distribution given enough noisy samples. The reason this works, just to give you a hint, is that like basically what happens, I have two random variables and I add them. What happens to the densities? They're getting convolved. Now, if you had infinite samples, you could perfectly learn the convolved density of your measurements, and then you could get to the Fourier space and do the deconvolution and get back the measurement, the density that you care about. So there is some
so there is an inverse convolution.
I mean, yes, information theoretically, when you add Gaussian noise, you can do this. But in order to do this, you need to perfectly learn the density first, then go to the Fourier space, then divide it by the density of the Gaussian, and then do the inverse Fourier, and then you do this. So of course, this is like, there is an algorithm that could do this given infinite samples, but this is not a practical algorithm, right? So what we want to do is we want to basically go to problems that are solvable. So we're not doing the impossible. So we're not going to go and try to learn a distribution when it's not possible to do this, right? So we will only do this for corruption models that are like actually allow you to learn a distribution given infinite noisy samples, but we don't have good algorithms for this. So out of Gaussian noise is an example of this. There is an information theoretic argument that says that information is not lost. Of course, you need more samples, but given infinite samples, you can do this. So now we say, okay, we are operating in the regime where we have finite samples and we want to do diffusion models. How can we do this? And this algorithm is actually doing exactly that.
I see. Okay, that totally answers my question. I appreciate it. So I guess like one of the things to look at is sort of like what corrupting processes like kind of minimize how much high fidelity stuff you lose. Is that something that you guys are kind of looking into?
Yeah, so if you could design the corruption process yourself, this is a very interesting question. In some cases, though, like you don't get to design the corruption process. The corruption process is decided by
I guess that's true. Yeah.
You know, like when but as for example, in MRI, you get to decide like how, like, you know, like if you're not willing to have your patient sitting in the scanner for like 2 hours and you want them to sit in the scanner for like 10 minutes or 5 minutes, then you get to decide like which exactly corruption you're gonna have. And
cool. Okay.
Maybe this gives you like some sort of like flexibility in like how you should do a measurement design and that kind of stuff. But yeah, this is super interesting.
Gotcha.
We haven't looked into this, but I
Cool.
think it's
awesome. That answers my question.
awesome.
Thanks.
Okay, then go ahead. Let's just order Vidya.
Yeah, okay, thanks. Thanks so much for the presentation. I have some basic questions and some more kind of future directions questions. So if you could go back to the slide before this one.
Which this one?
Yeah, this one. Okay. So this is just like very basic question. So, okay, so you have only the kind of the T sub n noisy images, right? That's all you have.
Yes. Yeah.
Okay. And so how are you going, like how are you training? Okay, so then you have the H sub theta, which is your neural network, and then you're getting out this blurry image.
Yes.
So can you just kind of intuitively describe this like loss function? Like so you don't have this blurry image ahead of time, right? You're creating that somehow?
Right. So like all we have is a neural network we are training. So this H theta. So we're training this neural network for all times. And then we also have these images that from our data set that are in nature. So like, let's say that let's imagine that we are in the middle of the training. And then let's see what will happen. So in the middle of the training, you have managed to learn some H theta, whatever that is. So you can get the image from your training set, this XT nature, and then you can ask your neural network to give you like some prediction. Of course, in the beginning of the training, this prediction is not a blurry image, it's just some arbitrary bad image because you haven't initialized your neural network. But then somewhere in the middle of the training, the neural network has managed to learn kind of this stuff, so it gives you like this blurry prediction. And then what you do is like you say, okay, I have this blurry prediction, I'm gonna keep it on the side. Then you take this noise image from your training set, and you also put it into the reverse sampling of this neural network that you have. So you kind of like the thing, one way to think about that, you are saying that, okay, I will assume that everything has been perfect so far, and then see what happens. So if everything has been perfect, I could get this blurry prediction, but I could also like run my reverse sampler and get these other intermediate like noisy versions. Of course, everything is not perfect because you are still training, but assuming that everything is perfect, this is what you would do. And then the perfect model would satisfy this consistency thing. So you would satisfy that like, for this like little, this image that have like less noise, if you take the prediction of the noise and you average them out for all of them, you should get like the one-step prediction. And then you see that this doesn't happen. This is violated. And you're like, okay, wait a minute. I haven't learned my perfect denoiser. My neural network is not correct because the perfect denoiser would make this loss 0 when my loss is not 0. So I'm going to take a gradient update to update my network such that like this is satisfied. And then you kind of repeat. So you're like assuming every time that like everything has gone perfect. You measure like this consistency loss. If everything actually went perfect, you have like this consistency loss being 0. If things didn't go as well, you have like some signal there to update your network to make it happen.
Okay, that's really helpful. Okay, so the one piece I still don't understand is how do you get those images at T prime?
This T prime, you run the reverse sampling. So you just basically run, like, let's say that you had your network that was perfect. You could just you just initialize the sampler from this T nature and then run the reverse sampling. Then we do the same with our not as well trained neural network.
Wait, so you have an inverse neural network as well?
No, it's the
that's
same.
forward denoiser. Yeah. Sorry,
Yeah,
forward noising process.
So yeah,
so
we have
you run the forward noising process on that blurry input from the first one.
No, sorry. Maybe I didn't say that correctly. You don't do that. So you run the reverse sampling. So there is the forward process that adds noise. We're gonna do the reverse one. So starting from this T nature, we run the reverse process from T nature to T prime. So that is like, take some steps. It's not a single prediction. It's like maybe 10 predictions of the neural network. And then after these 10 steps, we have this like image at T prime. So it's like, we use the network the way that we would use it during sampling, basically. So we run the reverse.
Okay, I understand. Okay, and that if we run it through so H sub theta is supposed to be just one step to the end, and we should run it on any. Okay, I understand. Okay, that makes sense. Thank you. Okay, and my other question. Oh, go ahead.
No. H theta is the one-step prediction. Then these curves, this like yellow curve and this blue curve, correspond to many calls to H theta that are running the reverse process. So yeah, perfect. I think you got this.
Okay, okay, that makes sense. Thank you. And my other question is kind of your future directions for kind of the arbitrary corruptions.
Yep.
Okay, like after.
Yeah.
Okay. Yeah. So for this one, okay. So you're saying you don't know the corruption model at all. So
Yes.
okay. So what I do is I do like inverse problems where I know the corruption model. I mean, maybe I have like some things about my corruption model like slightly incorrect, but I basically know the corruption model. But it's like totally nonlinear. It's like there might be like instead of measuring amplitude, I'm measuring intensity, stuff like that. So it's nonlinear, and it's like some like weird form. There's like Fourier transforms, or there's like other transforms in it. So okay, so basically I'm asking, can I use this method for this problem?
Yes, you can. Basically, like you have some corrupted measurements. Maybe you even know like kind of how these were corrupted, but you don't know how to revert it, of course. It's not invertible.
Right.
And you're like, okay, these are are not clean, so I don't want to use them as clean. What I need to find is my corruption that's like highly nonlinear and stuff, gives me some images, or like whatever this data point, whatever this modality is. And then I have this like clean thing that I don't have access to. But after adding a lot of noise, at some point, there is a point where like after adding noise, these two become equivalent. So what you need to decide, basically for each one of your measurements, how much noise should I add to make it look like a good thing plus noise. So you have the bad thing plus noise and the good thing plus noise, and you need to basically find the minimal amount of noise you need to add, such that the good plus noise is the same as the bad plus noise.
Okay, so but okay, so one thing is that, okay, let's say it's like, I have some Fourier transform, my measurement in some Fourier transform, right? I'll never be able to add enough noise to make it look like the thing I want, right? Because the thing I want is the Fourier transform of my measurement. Like, how will I add this noise?
So you have like you have some original measurements in the Fourier space or in the no Fourier space. Like what are you trying to get? You're trying to get the Fourier space.
Okay, let's say, okay, so one example of like some problem I study is like crystallography diffraction. So I have my diffraction images and I want to get my protein structure.
Yeah. So great. I mean, actually, we're super interested in that particular problem as well. So I think we should talk more. But
okay, maybe we can talk offline too.
But yeah, but generally the idea is that yeah, like you need to corrupt further your measurements, the ones that are corrupted, to make them look like to make them look like real images, real points plus corruption. Of course, maybe in the limit you need to add like infinite amount of noise to make that happen. But for practical purposes, in order to distinguish between the two, maybe we don't have algorithms, so maybe it's good enough. So there is a point that is not in the infinite limit of infinite noise, where like you add some amount of noise and then you use them as clean plus noise. And then if you also have some clean data, then things are gonna go fine, I believe. If you don't have any clean data and you just do this, maybe it's gonna become a little trickier. But given some clean data and a lot of measurements like this, I think this method should work. But yeah, we can talk more offline if you want. Like I'm very interested in this particular problem, so I think we should talk in more details about this offline.
Okay, let's talk more offline and let other people ask questions. Thank you so much.
Thanks so much.
All right, Nico.
My turn. I hope you can understand me.
Yeah.
Okay, great. So my first question is whether during training the model actually knows which sample is sort of unclean and which sample is clean during your experiments.
For which setting? Like generally when we train the model, we just give it the corrupted sample and the amount of noise that has been added. So this is like what the model knows. Nothing else. It tells you like you give it a noisy sample and then you tell it it's a noisy sample at this particular noise level.
Okay, I understand. And my second question is, have you compared different sizes of data sets, and does that change sort of the amount of how much noisy data you can use? Does that change the ratios of noisy and clean images in terms of usefulness?
Oh, you are asking like maybe some data points that could be more useful to, like maybe some data points we don't want to noise them because they're like more distinct maybe and we want to learn them, and some others it's okay to noise them. Is that kind of the direction that you're asking?
No, it's rather in the direction of if you have more and more data, even in general size of data set, have you sort of looked at how much the ratio changes between how useful clean and dirty data gets?
Right. Yeah, right. Okay, yes. So so for example, okay, got it. Thanks. That's a great question. So we train data sets, we train models on CIFAR10, CELEB, and ImageNet. So that gives you a range. So CIFAR10 is like 60,000 maybe. I think CELEB was 30,000, and then ImageNet was 2 million. And then the prices, they don't change that much when you have clean as well. There is a difference. So we do have the exact numbers in the paper, but they don't change so much. I think that the bigger the data set, the more valuable the noisy samples become, assuming that you still have like this fraction of like clean samples. Now, if you don't have clean samples, I don't know how this works in terms of like what are the prices. But yeah, just to answer the question very, very fast, it's like for bigger data sets, noisy samples seem more valuable. That's what I would say.
Okay, thanks a lot. And that's pretty interesting. Actually, I thought it would be the other way around. But thanks a lot for your presentation.
Of course. Of course, perfect.
All right. Then thanks. And I think we should connect a bit with Vidya.
Sorry,
Yeah,
Hannes, could I have a really quick question?
sure. Go ahead.
Really quick. I just had this idea, but I don't know if it's applicable or not. Suppose you have a human demonstrations, right? They're by definition they're imperfect. Like it could be a drawing of something imaginary or demonstration of trajectory. Would something like that would be applicable to get back to a perfect, underlying thought from an imperfect human demonstration?
Right, yes, perfect. Like basically this kind of framework should be useful across the board when you have imperfect data. Now, this imperfect data, they can arise from some scientific application where like you had like some, I don't know, you didn't have clean data for scientific reasons, or it could be that like there are like corrupted data because you generate them with a neural network, not you didn't get them from the data set, or it could be that like humans gave you some like data, but humans also made mistakes, so they're like imperfect. So can you actually get like human annotations that are imperfect and do better than humans? I think all sorts of these questions are super interesting. We have like briefly touched upon some of them, but I would say that like now it's the exploitation phase of this like kind of direction. So we're more actively like looking into like setting which of these regimes this works the best. And maybe, yeah, learning from imperfect human annotations would be a very good application of this.
Okay, then we have a question in the chat about the noise type. Does Tweedie's formula and consistency loss work for other noise types other than Gaussian noise? I think
So yeah, go ahead, Anders.
I think Tweedie's formula is like a statement about specifically Gaussians. So if you convolve something, then, okay, I guess the question is then, is there sort of an analog of something similar for other, let's say I have a student T that I convolve with or whatever.
For all the distributions that have density in the exponential family, there is a generalization of Tweedies. So there is some generalization of Tweedies that works for all the distribution in the exponential family. And I think there are some Tweedie-like versions for even things that are not in the exponential family. But this gets a little bit more tricky, I think.
What type of noise might one care about that is not from an exponential family?
I don't know, like maybe more like discrete, like jump process and stuff, like more like kind of things like this.
Okay.
So for jump process, I think there is also some sort of like, I'm not too familiar with the literature, but I think there is some at least high level analog of Tweedies.
Yeah. All right, then I'm calling it a wrap here. And yeah, thanks Janice. Thanks everyone for the nice questions. And especially Vidya, I think your questions warrant further chatting. That sounds very interesting. But yeah, then see you, Friends of the Sun, next week, hopefully. And have a nice time until then. Bye.
Yeah, thanks a lot.